Hello, and welcome to the third annual Global Heat Flow Day. Thank you for joining us. This video will provide an introduction to the structure of the International Heat Flow Commission's Global Heat Flow Database. The structure of the Global Heat Flow Database was defined in 2023 through an international collaboration of subject experts. Within this work, a new quality assurance procedure was implemented. The new database structure was necessary to bring this valuable global resource into the modern digital era and to make the data available to more people. The last definition of the Global Heat Flow Database was provided in 1976 at the beginning of the modern computer era. As seen here, the entire entry for each data point was limited to only 80 characters. While this allowed for compact storage and use of the data, it did not allow for indications of quality, information on measurement methods, or other information critical to reuse of the data. The primary purpose of the database is to collect and provide heat flow measurements. Heat flow density is a derived measure calculated from measurements of the temperature gradient and the rock thermal conductivity, seen here in the original 1976 format. The database that we present today is a complete revitalization of past compilations that benefits from 80 years of global heat flow research and decades of advances in digitization and data science. It transforms over 1,400 diverse and important results into a much more usable and useful tool for understanding our planet and utilizing the warmth of the earth for the needs of society. As we saw before, the Global Heat Flow Database was defined in 2023 by a global collaboration of experts. The purpose is to document heat flow around the world by assessing each data point individually and subjecting each to a strict quality control regimen. This ensures a high-quality product which improves the reproducibility of scientific research. The new database has been dramatically extended from 18 to 62 individual database fields, and there are supplemental fields that allow inclusion of text information. The goal of the database is to provide information from the original scientific publications so that the data points are accompanied by contextual information and descriptive documentation. The database is interoperable in that it can be linked to other digital products and services such as cartographic services, geological maps, stratigraphic classifications, digital object identifiers, international geosample numbers, and more. The database is also interconnected in that it links directly to the database of related heat flow publications. Finally, it has also been built to facilitate linking to external relational database systems. Replacing the single data point at each location, as shown in the old database table a few slides earlier, the heat flow database is designed with a more comprehensive and flexible structure in mind. A single borehole may have multiple measurements over many years, carried out by different scientists, in which different projects may have measured different parameters or used different methods for data collection. To better represent all the data that have been measured at a single location, a parent-child structure has been implemented here, which more clearly shows the relationships between different measurements. This represents a fundamental change in the way that heat flow data are presented, as previous databases have required separate entries for each measurement and have not clearly shown the relationships between different measurements. The heat flow database links various data that are from a single location, so that the data can be more effectively used for a variety of applications. This slide shows how the parent-child structure works in practice. An entry in the database begins with a heat flow density value, Q, in a specific location. In this location, there may be multiple heat flow measurements included in the database. These may be from different depths and may represent a range of heat flow values, temperature gradients, and conductivities. A decision must be made to determine which one is used as the representative heat flow value for that location. This decision depends on the quality and completeness of the various data points. The chosen value is known as the parent. For this figure, these two are the children, and this one is the parent. Every heat flow measurement can be affected by various factors, including paleoclimatic effects, topography, erosion, convection, sedimentation, heat refraction, and whole bottom water, as well as heat production of the overburden, H. These effects must be considered in the final calculation of the heat flow value and should be corrected for if they are affecting the heat flow and if you have measurements of them. The database provides fields for recording whether each of these effects has been corrected for or not. Basic information about the site is included in the metadata at the parent level of each record. For each child entry, you have heat flow, which is calculated from temperature and conductivity, and there are other data and metadata which are related to site-specific conditions. We will learn more about each of these in the subsequent slides. This diagram shows how data and metadata are organized in the database. The parent level includes the primary heat flow value and its uncertainty, which are two mandatory elements. The descriptive metadata contains 11 mandatory, recommended, and optional elements about the collection site and measurement method. Under the parent level, the child level, in green, contains multiple heat flow measurements that have been made at the single location. Each child entry provides the data that allows calculation of the heat flow value plus additional metadata and flags. There are 29 data elements in each child entry, divided between heat flow, conductivity, and temperature. These include calculation methodologies for the final heat flow, conductivity, and temperature values, plus much other valuable and relevant information. In addition, there are 20 metadata fields to provide additional contextual information to the data, including flags for corrections that have been made to the final heat flow value, lithology, and more. There is no field for radiogenic heat production. This information is recorded in the database as a metadata flag. The metadata scheme used in the heat flow database comes from metadata variables included in databases for boreholes, mining, and probe sensing applications. This is an enhancement that allows descriptive information and context to be provided directly in the database instead of being required to go back to the publications for even basic information. Here we look at the actual heat flow database. Starting on the left side, you see the parent data, P1 and P2, the primary heat flow value and its heat flow uncertainty, as well as the parent metadata including site name, latitude, longitude, and elevation, as well as the basic geographic environment, which is whether the measurement was made on land or in water, and whether you are on the continent or in the oceans. Also noted here are whether the field is mandatory or recommended. You see this by the M or R in row 2. The units of measurement are also noted here. As you keep going right, we see the associated metadata for the parent level, including the general comments and additional details related to the parent data. Further to the right, we enter the child level. Again, we have mandatory and recommended data and metadata fields, including the heat flow value for the child and its related uncertainty, the method for deriving the heat flow value, plus other information for the child entry. You can see that this is much more extensive than the 1976 database. The publication reference is also provided here, along with a DOI as well as a data reference if the data itself have been published separately. There are a number of mandatory flags related to whether erosion, paleoclimatic, and other effects are corrected for in the heat flow value. There's a place to record the name of the expedition or the research project through which the data were collected, as well as information on the probe and lithology, which is an example of an optional parameter. Additional example components are the method of temperature correction and the number of temperature recordings, as well as the date of acquisition and information on the thermal conductivity measurements, including the source of thermal conductivity values. So that wraps it up for the structure of the heat flow database. We hope this video has provided a useful introduction to the database and encourages you to enter new data and use the database for your heat flow related studies. Thank you for watching. We look forward to working with you.